How exactly do astronomers find the precise position of stars in the real sky at a specific hour? The secret lies in calculating the horizontal coordinates of the luminary through a special parallactic triangle. Using the law of cosines and the five-element formula, scientists compute the exact altitude of the object. This mathematical algorithm helps flawlessly determine the coordinates of any distant star above the horizon.
Welcome. Today, we're going to conduct a rigorous examination of one of the most fundamental tools in astronomy, the parallactic triangle. It's really the elegant geometric key that unlocks our ability to map the stars and find any object in the night sky. So here's our roadmap. We're going to start by framing the fundamental problem that astronomers face. Then we'll build the parallactic triangle piece by piece. From there, we'll derive the core formulas, put them to the test with a real-world case study on the star Vega, and finally, we'll interpret what our results actually mean. All right, let's begin by defining the core challenge that spherical astronomy sets out to solve. At its heart, it's a problem of translation, specifically converting between celestial coordinate systems. Think about it this way. A star has a fixed address on the celestial grid, right? That's its declination and hour angle. But for you, standing on a specific spot on Earth, that star is constantly moving across your personal sky. Its position for you is its altitude, how high it is above the horizon, and its azimuth, which is basically its compass direction. So the fundamental problem is, how do we build a mathematical bridge to get from the star's fixed address to its apparent location from where you're standing right now? Now, the solution to this problem isn't just some dry algebraic formula. It's actually something far more elegant, a geometric construction. It's a special kind of spherical triangle that we build on the canvas of the sky itself, known as the parallactic triangle. Okay, before we can build this triangle, we have to visualize our workspace. I want you to imagine a gigantic imaginary sphere surrounding the Earth. The Earth is at the very center, and all the stars, planets, everything are projected onto the inner surface of this sphere. This is the celestial sphere. It's on this grand stage that our geometry will unfold. Every triangle needs 3 points, 3 vertices. For the parallactic triangle, these are very specific and very important. First, we plot the zenith, which we'll label Z. That's the point on the celestial sphere directly over your head. Second, we plot the north celestial pole, P. This is the point in the sky that the entire northern sky appears to pivot around. And third, of course, is the celestial object itself, our star, which we'll call M. And there you have it, Z, P, and M. These 3 points form the vertices of our triangle. Now remember, we're on a sphere, so the sides of our triangle aren't straight lines. They're arcs of great circles, and each one has a very specific meaning. The arc connecting the pole and the zenith, PZ, is directly related to your latitude. The arc from the pole to the star, PM, is what we call the polar distance, and it's derived from the star's declination. And finally, the arc from the zenith to the star, ZM, is the zenith distance. This last one is crucial because it's directly connected to the star's altitude, which is one of the very things we want to find. The sides are only half this story. The internal angles of this triangle are just as significant. The angle at the celestial pole, vertex P, is exactly the star's hour angle. It's a measure of how long it's been since the star crossed the local meridian. And the angle at the zenith, vertex Z, well, that one is directly related to the star's azimuth, its compass bearing. You see how elegant this is? All the variables we're interested in are neatly encoded into the geometry of this one triangle. So, with our parallactic triangle fully constructed in our minds, we're ready for the next step. We can now bring in the powerful machinery of spherical trigonometry to derive the actual formulas that connect all these pieces together. Let's first figure out how to find the altitude. To do that, we're going to focus on the side ZM, the zenith distance. By applying a rule called the spherical law of cosines to this specific side, we can create a relationship between it, the other 2 sides, and the angle opposite it, which happens to be the hour angle. After we substitute the values of the sides for their astronomical equivalents, things like latitude and declination, and we do a little bit of trigonometric simplification, we arrive at this. This is the fundamental equation. It is the crucial link, the mathematical bridge we were looking for, that directly connects the star's fixed coordinates to its altitude in an observer's local sky. Okay, 1 down, 1 to go. Now we need to find the azimuth. For this, we'll use a different but equally powerful tool from spherical trigonometry, sometimes called the formula of 5 elements or the cotangent rule. This lets us solve for one of the triangle's angles, and the one we're interested in is the angle at the zenith, because that's where the azimuth is hiding. This manipulation gives us the formula for the azimuth. But I want you to notice something really important here. To solve for the azimuth A, you need to know the altitude, h, the very value we just finished calculating. It really shows you how solving this triangle is a sequential process. You find the altitude first, and only then can you find the azimuth.
All right, that's enough theory for now. Let's put this framework into practice. We're going to take on a very concrete problem, finding the exact position of the bright star Vega, as it would be seen from Rome at a particular moment in time.
So here's our data. Our observer is in Rome, at a latitude of 41.9 degrees north. The star is Vega, whose declination is a known quantity, plus 38.8 degrees. And let's just say, for this problem, its hour angle is 45 degrees. That just means it's been 3 hours since Vega was at its highest point in the sky. Our job is to use this information to calculate its altitude and its azimuth. First up, the altitude calculation. We take our known values for latitude, declination, and hour angle, and we plug them directly into that first formula we derived. After running the numbers, we find that the sine of the altitude, h, works out to be about 0.829.
Now we just need to take the inverse sine or arc sine of that number to find the angle itself. And there we have it. Vega's altitude is approximately 56 degrees above the horizon for our observer in Rome.
Next, let's find the azimuth. We take our second formula and substitute in the known values. But remember, we also need to include our freshly calculated altitude of 56 degrees. We plug everything in, do the arithmetic, and we get a value for the cosine of A of roughly 0.175. And for the final step, we take the inverse cosine or arc cosine of that value. The result is an azimuth of approximately 80 degrees. So we have our two answers, an altitude of 56 degrees and an azimuth of 80 degrees. Okay, so we've done the math. We have these two numbers, but what do they actually signify? If you were that observer standing in Rome, what do these results tell you about where to look for Vega? Well, these numbers give us a very precise location. An altitude of 56 degrees tells us Vega is high in the sky, more than halfway up from the horizon to the zenith, that point directly overhead. The azimuth of 80 degrees, measured by astronomical convention from the south point towards the west, tells you exactly which direction to face. It places the star squarely in the southwestern part of the sky. This is the magic of the parallactic triangle. It takes these abstract celestial coordinates and turns them into a tangible, observable reality for any person, anywhere on Earth.
And that concludes our analysis. What we've done here is use a method that turns the sky into a completely predictable map. But I want you to think beyond just finding stars for fun. This is more than a historical or academic exercise. Where else is this kind of precise positional calculation absolutely critical? Think about celestial navigation on the open ocean, or tracking satellites in orbit. The parallactic triangle isn't just a relic. Its principles are the mathematical engine behind countless modern technologies that rely on knowing exactly where something is in the sky right now.
Thank you, friends. Strive for understanding and become wiser. See you soon.